Hi, this is the first video for Chapter 9 about estimating the value of a parameter. So in this video we're going to talk about Section 9.1, which is about estimating a population proportion. So a point estimate is just a single value or point used to approximate a population parameter. In this section, since we're talking about proportions, we're going to talk about approximating a population proportion. So the sample proportion, which is represented by P with a hat on it, so we call it P hat, is the best point estimate of the population proportion P. And if the P hat value is not given to us in a problem, we can calculate it by taking x and dividing by n, where x is the number of individuals in the sample with a specified characteristic, and n is the sample size. Another way to think about this is if we think of a sample as a binomial experiment with n trials, then the sample proportion p hat is the proportion of successes. So it's the same as the number of successes, x, divided by the number of trials, n. Here's an example. In a Pew Research Center poll, 70% of 1,501 randomly selected adults in the United States believe in global warming. Find the best point estimate of the proportion of all adults in the United States who believe in global warming. So here, when we're asked to find the best point estimate for the proportion of all adults, that's asking us to find an estimate for the population proportion. The sample proportion in this problem is 70%, or if we write that in decimal form, it's 0.70. This is the best point estimate for the population proportion given the sample data that we have. Here's another example. In July of 2008, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. Obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. Again, what we're asked for here is a point estimate for the population proportion. So to estimate that population proportion, we're going to use the sample proportion from the sample data that we have. Our sample proportion p hat is going to be 1,123 divided by 1,783, or 0.63. This is the best point estimate for the population proportion of registered voters who are in favor of the death penalty for persons convicted of murder. Again, this is based on the sample data that we have. So let's talk about what confidence intervals are. A confidence interval, or an interval estimate, is a range or an interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated as CI. The confidence level of a confidence interval is the probability, 1 minus alpha, that the confidence interval actually does contain the population parameter, assuming that the estimation process is repeated a large number of times. When we're estimating a population proportion, again, the sample proportion p hat is the best point estimate of the population proportion p. But since the sample proportion varies depending on the sample selected, an interval estimate, or a confidence interval, gives a range of possible values for the population proportion, along with a measure of how good the estimate is, the confidence level. The sample proportion will be in the center of the interval. The distance the interval spreads on either side of the sample proportion is called the margin of error. Here's an example. In a poll, 70% of 1,501 randomly selected adults in the United States believe in global warming. Based on this sample data, our point estimate for the proportion of adults in the U.S. that believe in global warming is 0.70. The 95% confidence interval based on this sample data is from 0.677 to 0.723. The sample proportion is in the center of the confidence interval. The distance the interval spreads on each side is the margin of error. So what we're doing here, representing the confidence interval, is just giving the lower limit and the upper limit. And here's what it looks like if we graphed it on a number line. Here is our point estimate right in the middle of the confidence interval. Here is our lower limit for the confidence interval, which is 0.677 or 67.7%. Our upper limit is 0.7723 or 72.3%. And the distance on each side that we go from our sample proportion in the middle is the margin of error. So we're going from our sample proportion down by whatever our margin of error is, and also up. Now, to interpret this, the 95% confidence level tells us that the probability of our interval actually including the true population proportion is 95%. So if we selected 100 samples and calculated confidence intervals for each one, approximately 95 of them would include the actual population proportion. The way I like to think about it is that 95 out of the 100 would be hits and 5 would be misses. So let's suppose that the true population proportion is actually 71%. Then approximately 95 of the 100 intervals would include the value 0.71, so they would be hits, and approximately 5 of the intervals would not include the value 0.71, so they would be misses. So let's say that we took 3 more samples and looked at the results, and again we're assuming our true population proportion is actually 0.71. So here's one sample and the confidence interval. So for this sample, the sample proportion was 0.696. Again, that's in the middle of our confidence interval. And our confidence interval goes from 0.673 to 0.719. Here's the true population proportion. So this one would be a hit because the population proportion is included in that interval. So that one's a hit. Here's another sample. In this one, the population proportion and the sample proportion were very close together. So again, this one is a hit. Here's data from a third sample. In this one, our sample proportion was 0.736, and the interval goes from 0.713 up to 0.758. So this one actually doesn't include our population proportion of 0.71. So this one would be a miss. So first, the requirements for estimating a population proportion P. First, the sample is a simple random sample. Second, the conditions for the binomial distribution are satisfied, which means there's a fixed number of trials, the trials are independent, there are 2 categories of outcomes, and the probabilities remain constant for each trial. Third requirement is that there need to be at least 5 successes and 5 failures in our sample. Under these conditions, the sampling distribution of sample proportions can be approximated by a normal distribution. Now, the way we use that fact is that we use a z-score, which is from the standard normal distribution, to distinguish between sample proportions that are likely to occur and those that are unlikely to occur. A z-score on the borderline between these two is referred to as a critical value. So here's a picture of our normal distribution, our standard normal distribution. So we have a mean of 0 and a standard deviation of 1. So our critical values are going to be the ones that are on a borderline between sample proportions that are likely to occur and sample proportions that aren't likely. So anything in between these two would be the ones that are likely to occur. Anything in those two tails is going to be something that's unlikely to occur. Now, we'll need to find those critical values in order to construct a confidence interval. So if we have a specific confidence level, here's how we find our critical value. The alpha is the probability that the confidence interval does not contain the true population proportion. In other words, alpha equals 100% minus our confidence level. Then we take alpha and split it equally between the two tails of our standard normal distribution. The critical value negative z alpha over 2 is the cutoff value for the bottom alpha over 2 of the z-scores. So here's a picture of what we're doing. Here's our confidence level. We want that to be the probability that our interval does contain the true population proportion. So the complement of that is going to be alpha, and we're going to divide alpha equally between the two tails. What we're looking for is the values of z that separate these areas. And since our normal distribution is symmetric, we're going to have a negative z alpha over 2 and a positive z alpha over 2. Here's an example of finding a critical value for a specific value of our confidence level. So let's find our critical value for a confidence level of 95%. First, we need to find alpha. So alpha is just 100% minus our confidence level. In this case, that's going to be 5%. And we normally write alpha in decimal form, so that would be 0.05. This area is going to be split between the two tails, so we need to divide that by 2. So alpha over 2 is 0.025. So here's our picture again. Our confidence level is 95%. So that means we've got 0.025 in each one of our tails. What we're going to look for is these two values that form the borderline between those two, or between those three regions. Now to do this, we're going to use our calculator function inverse norm that we talked about before. And the easiest way to do this is to find the negative z alpha over 2 value. Because remember how your calculator function works, it assumes that you're going from the z value to the left. So this is the easiest one to find. All we have to do is put in our area in that left tail, which is 0.025, and this is the standard normal distribution, so our mean is 0 and our standard deviation is 1. If you put that in your calculator, you will come out with negative 1.96. So our value on the left side is negative 1.96. That means the value on the right side, which is the one we're actually going to use, is positive 1.96. So really all you have to do is take the negative off. Alright, so here's our picture with our two cutoff values. We have negative 1.96 on this side, positive 1.96 on this side. Now we're going to use all these things to find our margin of error for the confidence interval. So when data from a simple random sample are used to estimate a population proportion P, the margin of error, which we denote by a capital E, is the maximum likely difference between the observed proportion P hat and the true value of the population proportion P. The margin of error E can be found by multiplying the critical value and the standard deviation of the sample proportions. So here's the formula. Our margin of error is equal to our critical value, z alpha over 2, times the square root of p hat times 1 minus p hat divided by n. Again, the center of our confidence interval is going to be the p hat, and the distance the interval spreads on each side is e, the margin of error. So our confidence interval will actually look like this. Our lower limit will be p hat minus e, and our upper limit will be p hat plus e. Here's an example. Find the margin of error in the confidence interval for a proportion if p hat is 0.35, n equals 400, and the level of confidence is 95%. Now we already found that the critical value for a 95% confidence level is z alpha over 2 equals 1.96. For when we're working with confidence intervals for proportions, these values won't change. But once you have found a critical value for a specific confidence level, you can use that from then on. So our margin of error is going to be E equals 1.96 times the square root of 0.35 times 1 minus 0.35 divided by 400. Here we're just putting in the p hat and the n into our formula. So if we calculate that out, that turns out to be 0.047. So for our confidence interval, we're going to take our p hat, which was 0.35, minus 0.047 to get our lower limit. To get our upper limit, we take 0.35 plus 0.047. So our confidence interval goes from 0.303 to 0.397. The interpretation of this confidence interval is that there's a 95% probability, or we can say we're 95% confident, that the true population proportion is between 0.303 and 0.397. So here's the picture of our confidence interval. Again, our sample proportion, the 0.35 is right in the middle. Here's our lower limit, and here's our upper limit. And we're saying that we're 95% confident that the true population proportion is somewhere in this interval. Here's another example. In our Pew Research Center poll, 70% of 1,501 randomly selected adults in the United States believe in global warming. Construct a 90% confidence interval estimate of the proportion of all adults in the United States who believe in global warming. Again, what we're being asked for here is a 90% confidence interval for the population proportion. So first we would find alpha. Alpha is 100% minus 90%, so that's 10% or 0.10. Alpha over 2 would be 0.05. Then again, to find our critical value, we'll find the negative z alpha over 2 and then just take off the negative. So that would be inverse norm of 0.05, which was our alpha over 2, with 0 for the mean and 1 for the standard deviation. And that gives us negative 1.645 on your calculator if you round it to 3 decimal places. So our critical value that we will use is positive 1.645. In this problem, we were given the sample proportion as a percentage, 70%, so we'll change that to a decimal form as 0.70, and our n, oops, sorry, typo there, our n is 1,501. So our margin of error is 1.645 times the square root of 0.70 times 1 minus 0.70 divided by 1,501. And that turns out to be 0.019. So our confidence interval is, our lower limit is 0.70 minus 0.019, our upper limit is 0.70 plus 0.019. So our confidence interval is 0.681 up to 0.719, or from 68.1% up to 71.9%. And the interpretation of this is that we are 90% confident, or we can say there's a 90% probability that the true population proportion is between 68.1% and 71.9%. Here's a third example. In July of 2008, a Quinnipiac University poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. 1,123 were in favor. Construct a 99% confidence interval to estimate the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So again, the first thing to do is find alpha. Alpha is 100% minus our confidence level, which would give us 1% or 0.01. Then we divide alpha by 2, which gives us 0.005. Our negative critical value is inverse norm of 0.00501, which would give us negative 2.576. So the critical value we use in the formula is 2.576. Our p hat we actually have to calculate here. It's the number that said they were in favor of the death penalty divided by the total sample size, so it's 1,123 divided by 1,783, so that's 0.63, and our n is our sample size. So our margin of error, if we calculate this, turns out to be 0.029. So to get our confidence interval, we take our point estimate, or our sample proportion, minus the margin of error, and our sample proportion plus the margin of error. And that gives us from 0.601 up to 0.659 for our confidence interval. So the interpretation of this is that we are 99% confident, or we say there's a 99% probability that the true population proportion is between 60.1% and 65.9%. So when we're determining sample size, here's how we look at it. Suppose we want to collect sample data in order to estimate some population proportion. The question is, how many sample items must be obtained? In other words, what's the sample size that we have to have? So if we take our margin of error formula, which looked like this, and solve it for n, the sample size, here's what we get. We have to square our critical value and then take our p hat times 1 minus our p hat and divide by our margin of error squared. Now the problem with this is that we don't have p hat unless we've already collected the sample data. We can't collect the sample data until we know what sample size to use. So in order to be able to use this formula, we need some kind of estimate for our sample proportion. So what we end up with is two different formulas for our sample size, depending on what situation we have. So our minimum sample size necessary to construct a confidence interval for P with a margin of error E is this one. We take our critical value and square it times P star times 1 minus P star divided by E squared. And this is where P star is a prior estimate for our sample proportion. In other words, if there was a prior study done, if we have some kind of way of estimating what our sample proportion might turn out to be, then we would use it in here. Now, if we have no idea, or if a prior estimate isn't available, then we assume the most conservative case, which gives us the largest sample size, and that would be when P star is equal to 0.5. In other words, if we have no way whatsoever of estimating our sample proportion, then we go with the most conservative estimate, which is that our sample proportion is just 1/2 or 0.5. In this case, the formula is a little simpler. We take our critical value and square it times 0.25 and divide by E squared. One thing to remember when using either one of these formulas is that since we're talking about proportions, everything has to be in decimals. So that includes the margin of error E. If you're given the margin of error as a number of percentage points, you have to put it in this formula in decimal form. Here's an example. A manager for eBay wants to determine the current percentage of U.S. adults who now use the internet. How many adults must be surveyed in order to be 95% confident that the sample percentage is in error by no more than 3 percentage points? For part A of this question, we'll use the fact that a previous survey in 2012 found that 83% of adults use the internet. For part B, we'll assume that there's no prior estimate for the sample proportion. So for part A, we already found a critical value for 95% confidence interval is 1.96. In this one, we're using our prior estimate of 83% or 0.83. And our margin of error that we want is 0.03. That comes from up here where we said we wanted the sample percentage to be in error by no more than 3 percentage points. 3 percentage points is saying 3% for our margin of error. So again, we have to convert that to a decimal form. In this case, since we have a prior estimate, we're using the first formula. So we have 1.96 squared times 0.83 times 1 minus 0.83 divided by 0.03 squared. And that gives us 602.3. Now, since we're looking for our minimum sample size necessary in these problems, we always have to round up to the next whole number. So we would round up from 602.3 up to 603. That's the minimum sample size necessary using this prior estimate for p-hat. Now in part B, if we assume we don't have a prior estimate, we're going to use the other formula. So we would have our 1.96 squared times 0.25 divided by 0.03 squared. This one gives us 1067.1, which we would round up to 1068. Notice how much bigger this minimum sample size is than the one we got from using the prior estimate. That's what I meant about this being the most conservative way to do these problems. It gives us the biggest sample size.